Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Good morning, everyone. For me, it's a great pleasure to introduce the speaker of the second talk of our mini seminar today, Professor Walter Kellerman. I don't think that I have to do long introductions here. He is well known as a valuable contributor to audio and signal processing. We know that he is currently chairman of the Technical Committee of Audio Electroacoustics of IEEE Signal Processing Society. He is a distinguished lecturer in IEEE, but for many of us, he is just Walter Kellerman, the enthusiast who brings new algorithms, new ideas, constantly tries to improve this or that particular algorithm in acoustic echo cancellation, in noise suppression, in microphone arrays. Constant participants of the conference. We really love to participate and to take part of. So without wasting too much time, Professor Kellerman has the floor.
Thank you, Ivan, for this very nice introduction. And as all of you know, the main work is usually done by the students. And this is the list of students I want to recognize first before I start my talk. And some of you will know Robert Eichner, and he promised to join us today. He is with Microsoft since about a year and is working on in acoustic signal processing, which is the first line of the title. The next one is, of course, some buzzword. But the main thing is, of course, the multi-channel aspect of what we want to look at in this talk. And I would like to start with a brief introduction, and I apologize already that it's not going to too much into details in this talk. I would like to focus on the general scope of this area and also on some specific solutions, of course, in order to make you believe that something works at least. So the goal is pretty simple. It's an ideal seamless human-machine interface, which means these users here in an acoustic environment should be untethered and they should be mobile. And we foresee a number of loudspeakers and a number of microphones to do some signal processing. And the signal processing should fulfill the following tasks. Namely, first, it should reproduce signals for the listeners at their ears in the way they like it or we would like them to listen to. And the other tasks are basically to capture source signals and to determine the source position. So you see already we have a reproduction problem and we have a signal acquisition problem. And the fact that it's a problem is due to the acoustic environment here, which creates feedback between the loudspeakers and the microphones. We have reverberation, and reverberation comes in two flavors here. Usually, and John McDonough alluded to that already, of course we have the reverberation here when picking up the microphone signals. And the second flavor is the reverberation that we hear when we are listening to loudspeaker signals. And basically this is something which we mostly ignore, but I will come to that later. It's a perceptual thing that needs to be addressed in reproduction systems. Especially if it's high quality. And finally, we have, of course, noise and interference. And we want to address all these three problems in the following. And one of the real problems is that in many scenarios, you have all of these problems together simultaneously. So signal processing needs to look at it simultaneously. You all know many of these applications. I categorized them into two classes. One is basically hands-free equipment for telecommunication and what I call here natural human-machine interaction, which includes, of course, speech recognition. And you find them in mobile phones, cars, with desktop computers, but also for telepresence systems. And this is an area which I especially like because there you may have more money to spend on microphone and loudspeaker arrays, which is not the case, for example, in cars and mobile phones. And of course, then there is all these smart applications like smart meeting rooms, smart homes, and sometimes you look at museums and exhibitions as well. The second class is audio communication, and This means here we look at equipment for stages and for recording studios, and also virtual acoustic environments, for example, virtual concert halls or teleteaching studios. And with regard to the teleteaching studios, you may think of musicians practicing in two different places together. This is a very nice problem. There you can, the requirements are pretty tough, and that's something to look at in the future, which is very challenging. And of course, there's a more secretive application, which is surveillance. And as you can see, I don't put too many sub-items here for the same reason. Okay, let me show you a few microphone arrays which we built. And actually, when I joined the university in Erlangen, we started with a project on microphone arrays for laptops with Intel at that time. And here you see a microphone array of 8 mics, which will be used for beamforming in the following, and to illustrate the beamforming algorithms in the sequel as well. Then actually Robert Eichner worked in a European project, where the environment got a little more challenging. Namely, it was hands-free communication for emergency cars, like fire brigade cars, where there's a lot of noise, there's a lot of tension with the speakers. And obviously, this is only a reference microphone, so this is not to be used in practical applications at that point. So the microphones are here. We use microphone arrays also for interactive TV applications now in a recent European project entitled DITSIT. And what you see here, we have a large array, and you see logarithmically spaced sensors here along a long line. Actually, the whole array is about 1.5 meters. So that's for large screen TVs as well. And here you see another application for localization, actually. In a parking garage. I hope the image is not too dark for you, so that you can see the array here and here. And this is meant for localization purposes in highly reverberant environments, like parking garages, for example. Another application of surveillance would be public spaces. And here you see another microphone array with a total of 6 sensors. And here we have a very small one, which is also used for multiple source localization. It's only about 10 centimeters of diameter.
That public space, how do you use that?
Basically, you can use it for surveillance purposes, so that you immediately can steer a camera to when somebody smashes a window, for example. It's for mostly for bad guys, right? And that's, of course, I only show the civil applications here. Okay, then I always like to show a picture which is a microphone array which I did not build. That's the one by Gary Elko here. And I always use this in order to illustrate what also could be done but has been forgotten over past years. This is an array which basically is meant for communication between several auditoria. And this was at the high times of Bell Labs when they built this 360 element array for basically picking up the sound in the auditorium and being able to broadcast questions to the other auditorium as well. So you did not need a person to run around and put a microphone to the asking people. So you could use this microphone array. And that is actually back from the 80s. And during my PhD time, more or less exactly 20 years ago, we digitized that by putting a DSP just behind each sensor. And it was one of the first generation floating point DSPs. Some of you may know. On the reproduction side, yeah? That was actually, originally it was full bandwidth for audio, but we only use telephone bandwidth for evaluation. So it's 8 kilohertz. In that, yeah. Oh, that was a lot of data, actually. Yeah. We had cubic meters of hardware. You may ask Gary for the details. Okay, then on the reproduction side, we look into wave field synthesis for a few years now, and actually this work is mostly done by Rudolf Rabenstein, who's also with our chair, and he's basically trying to recreate acoustic wave fields, not just in a sweet spot, but in an extended area. And this, for example, would mean here in this area, which is enclosed by this rectangle. But you can have these loudspeaker arrays also in that fashion. Basically, you use these panels, and each of these panels is essentially an 8-channel loudspeaker. So you have 8 exciters behind these panels. And this was supported by the European Union also within the project of Caruso a while ago. This is just for introduction. Now let me move over to the more generic stuff in terms of equation. And I would like to look at the fundamental problems that we face here for reproduction and acquisition. And then I would like to show some advances in our group, mainly in the area of signal acquisition. And that looks at multichannel acoustic echo cancellation, at beamforming. I apologize for using beamforming. But we also look at blind signal processing, and then you may think of all your higher order statistics. And we published a while ago a concept which we think is quite generic, and we entitled it Trinicon, that can be used for source separation, de-reverberation, and source localization. And actually you can see it as a more general theory as incorporating supervised filtering like adaptive filtering and beamforming, like echo cancellation and beamforming as well. And finally, I will briefly look at source localization in the wave domain, and then I will come back to one of these examples of microphone arrays that you've seen already. So let me first start with the way we describe these problems. And basically what we assume is that we want to do linear signal processing on our 2 kinds of signals that are of interest for us. So we have a set of reproduction channel U, and we have a set of signals Z that we want to extract. And if you think of the inputs and outputs to this digital signal processing unit here, you have these loudspeaker signals as outputs and the retrieved signals as input, as other set of outputs. So we put those 2 in the output vector, and we, as this should all be linear signal processing, we assume that a set of input signals U and another set of microphone signals X is processed as inputs, and this G captures all the linear signal processing, which is of course multiple input, multiple output. Then you can look at this G in terms of submatrices connecting these inputs, the reproduction channels, and the microphone signals individually. And so you have these 4 submatrices, which we will use in the following to describe the problem. And then the goal is essentially to provide the desired listener's signals at the ears here. And if you describe this in terms of linear systems theory, you see you have the convolution of the loudspeaker signals with the acoustic environment, this MIMO system described by this matrix here, and you have the additional noise. This W, of course, captures 2 signals per listener in our case. And on the other hand, we have the microphone signals, X, which are basically a mixture of the source signals convolved by the acoustic environment, the impulse responses again, plus the acoustic echo resulting from the loudspeakers transmitted via the acoustic environment, plus the noise vector, and X, that's for the noise sector. And one of the problems, or one of the reasons why this is a problem at all, is that the acoustics can be quite nasty. So all the elements in our matrices here, H, they are basically impulse responses, and usually you characterize them by a reverberation time, and this is the time the sound needs to decay by 60 dB if you refer to T60, and this is in cars approximately 50 milliseconds, and in concert halls it reaches up to 1 to 2 seconds. Whenever you want to model these impulse responses, you take usually FIR filters with a number of coefficients that is typically T60 times the sampling frequency divided by 3. That captures basically enough energy so that the model error is below 20 dB. These models are inherently non-minimum phase, and if you look at typical impulse responses here and you look at pole zero diagrams, you see most of the zeros are actually on the unit circle. So in this case, it's an impulse response recorded in an office with a T60 of about 300 milliseconds at a sampling rate of 12 kilohertz. This is the impulse response, and you have actually thousands of zeros on or very close to the unit circle, which tells something about how to deal with this in order to, for example, de-reverberate it or also equalize it. Yeah.
Why is it non-minimum phase?
You have a flat delay from the source to the microphone. That is non-minimum phase.
No, non-minimum phase.
Non-minimum, right. It's non-minimum phase system. Any flat delay is non-minimum phase. Okay. So if we look now at the problems that we have to solve, given these acoustic environments, then we, of course, in reproduction, want to look at the desired signals at the ears. So basically, what we want to do is we want to create a set of desired signals, WD here, which is, of course, related only to the reproduction channels by some matrix HD. And this is basically the desired matrix that we have to provide in the end. And if we equate this to the actual path from the reproduction channels to the ears, then we have to essentially equate this HD to this term here. And you see, in order to provide this, you have to deal with the noise, of course. You still have the noise at the ears. And as a handle to that, you can use the microphone signals. And of course, as a second component, you see that the path for you must be the desired path, and this is in reality this acoustic part and the one submatrix that you have to condition the the signals that are to be reproduced, this GVU. So we have essentially two subproblems. One is an equalization problem, which you may look at as a deconvolution problem. So this unit must equalize this acoustic path in order to achieve the desired characteristic. And the second problem is an interference compensation problem, which basically means you have to use these microphone signals and create an estimate of the noise at the ears that can be fed into the loudspeakers. And of course, this also has to account for this acoustic path. Obviously, this is not so simple, and because you have to blindly identify the acoustics here between the loudspeaker and the microphone, and also you have to identify the noise component at the ears, which is also non-trivial. This is a real challenge, and all the active noise cancellation approaches we know so far always assume that they can measure the noises close to the ears. But this is in practice in our desired environment not possible, because we want to be seamless and people should not need to wear any devices close to the ears. Okay, let me briefly look at the state of the art in reproduction, and you just in terms of this description. If you look at conventional stereo and multi-channel systems, there is nothing like interference compensation, and also equalization does not consider the real acoustics. It only considers something which you may like as a listener. You boost the basses or change the amplification in various frequency bands, so you have frequency selective gains, but no accounting for the acoustics. If you look at beamforming with loudspeakers, that can be done either in a more conventional way or a superdirective beamforming, or also ultrasound based. But still, there is no interference compensation so far. And also, there is often only a coarse room equalization for a sweet spot, but not for a whole extended area where people might want to move while listening. What can be done, and is done actually in some products already, is that they use impulse responses for the desired characteristic already, so that there is a rough equalization already, but there is no room characteristics inversion or equalization directly. The furthest we come so far is wave field synthesis, and there are first attempts for interference compensation. So actually Achim Kunz started to work on this in 2004, but most of the time in practical environments it's still not possible to, for example, follow the time variance of the acoustic environment. And on the other hand, there are some results on equalization, but also only for time invariant room acoustics, and Sascha Spors works on that for about 4 years now. But most of the time this is also, even in wave field synthesis, just a set of impulse responses that are used for the reproduction channels in order to mimic sound artificial rooms without accounting for the real listening environment. So you can listen to sounds like in churches, but you don't really invert the local listening acoustics. Okay, there are quite a few challenges involved with that. One is the equalization, and the other is the interference compensation. And both, if you want to do it correctly and perfectly, require blind identification of these acoustics. And this is something which is still pretty far out of reach, I would say. But it's, of course, a nice challenge for academia. One problem, however, is that many people argue we may not need that, actually. We don't need that much spatial realism. We maybe not really need all the identification problem, which is highly sensitive to errors. And we published papers on that, how sensitive that is. So it's really questionable how much spatial realism can we really appreciate. And this is one of the questions that is still open in this area. And so maybe that's also one of the reasons why not so much effort is devoted to this.
Even if you could identify the system perfectly, though, if it's minimum phase, you can't invert it, right?
Right. You have to have an estimate for that. But as the listeners are usually not really sensitive to all-pass filtering, and you know any filter can be decomposed in an all-pass and a minimum phase system, so then it would be sufficient to equalize the minimum phase part. So you cannot perfectly identify that in many cases, right? But if you have a good guess for the all-pass filter, that might be sufficient. Okay. Let me turn to the signal acquisition part. And this is where we are quite sure that it's reasonable to identify the systems that we need to identify. Here, the problem is that we essentially want to extract a set of desired signals out of this acoustic scene, and they should be undistorted in the sense that they should sound as if you put a microphone very close to the mouth here and removed all other effects. So if you compare this to what you really get, of course, you have these microphone signals. As I said, this is a mixture of the source components, the acoustic echo and the noise. And this can be treated now by using your other inputs, namely the reproduction channels. And of course, then you have these two submatrices, GZU and GZX, this one and this one, to treat the microphone signals and to get what you actually want to get. This results in essentially three sub-problems. One is the acoustic echo cancellation problem, so where you essentially need to model this acoustic path, including those matrices here, by this matrix. And once you equate those two paths, then of course the acoustic echo is gone. That's basically what you want to do. So you want to remove all components that are related to your production channels. The second problem is the source separation and de-reverberation problem that essentially treats the components resulting from the desired sources. So what you get here at the microphone is the set of the mixture of all the desired sources, each convolved with the acoustic path impulse response, and you can treat that with the matrix GZX. And what the result should be basically a flat delay of the desired sources. And finally, you would like to suppress all the interfering noises, and this means essentially that this matrix should nullify all the noise components. This looks very simple, but of course GZX has also to fulfill this and to fulfill this. So this is basically a problem that this GZX needs to satisfy all of them, all of the requirements. And of course, one of the problems that you don't see so easily is that, first of all, you'd have to separate all these various components in the microphone signals. And this is also to be done by G. Okay, now after talking so much about problems, I would like to come a little bit to a few solutions. One is the multi-channel acoustic echo cancellation. And here we start with an isolated single channel case in order to define the problem again. Essentially, this is a textbook problem. Since 25 years, it has been recognized as such. And what you have to do is you find a filter which mimics the impulse response via the loudspeaker, the acoustics, and the microphone in order to remove the components of U. You do this, as you know, this acoustic environment is time variant by an adaptive filter which usually approximates the Wiener solution. I'm sorry for using second order statistics here, but this is quite appropriate and has been working for many years also. We actually use some higher order statistics in robust filtering as well. But for here, it's sufficient to assume we have adaptive filters that approximate a Wiener solution. Why is this a problem at all? Why do people talk about it? And I've seen a talk by Microsoft people at iWink on the problems on implementing this. It's a long filter, right? Typically to get 20 dB echo suppression in a conference room at 12 kilohertz sampling rate still asks for 1,000 or more coefficients. In a living room, it's easily 4,000 coefficients you would like to realize in order simply to mimic this or model this acoustic path. The multi-channel case is a little more complex because of two reasons. The one is you have, of course, obviously, if you have K loudspeakers, you have K times more filter coefficients to adapt, which makes the problem computationally more expensive. But the real problem for academia is, of course, that the autocorrelation matrix here, which is decisive for the adaptation speed and the adaptation behavior of the adaptive filters, is worse conditioned than in the single channel case. And I try to illustrate this here by this matrix. In the single channel case, you see a diagonal dominant matrix, and this matrix is the autocorrelation matrix of the state variables of the FIR filter. And usually it's at least diagonal dominant because also speech has a decaying correlation over it. So this would look like this. If you have 3 channels, most of these channels are correlated. So you can easily imagine in stereo a 5.1, the individual channels are strongly correlated. And then the autocorrelation matrix of the set of all input vectors for all these filters looks more or less like this. And if you just infer visually, there's a lot of regularity, and you find columns and rows which are very similar because the diagonals in the off-diagonal matrices are still similar to the main diagonal. So this matrix is usually pretty ill-conditioned. There are a couple of solutions to these two problems. Regarding the cross-correlation between the channels, there are basically only bad solutions. So whatever you do, it's somehow affecting your loudspeaker signals, because correlation is something you cannot remove by linear time invariant processing. So you have choices. Either you add some nonlinearity here, and of course this must be inaudible, and unfortunately the more inaudible it is, the less it helps, right? But that's quite natural. And you can add noise and the same holds, right? So you should use it below the masking threshold of the ear so that people buying very expensive audio equipment, $20,000 loudspeaker equipment, they should not hear any noise, right? But it still must be strong enough to decorrelate the signals, which is a dilemma, right? The third one, and we think this is the best solution, is to introduce time-varying all-pass filtering, which are tuned such that the perceived sources don't move in space. So you have different all passes here. They are time varying. So actually, they slightly move the sources. If you have a stereo reproduction, you would think that if you change the phases of the signals, the sources start to move. Actually, they do, but they do it only to the extent that you cannot hear it perceptually. So your binaural hearing is not as high, resolving that high that you can hear that. And this is actually done with the audio coding people. So you see Jürgen Harris' name here. He was an intern at that time with us, and then we developed this method. And we think, and we published that actually at ICAST 2008 or 7. This works actually quite well. So this is one way of playing dirty tricks to resolve this correlation problem. And here is the solution, or at least one solution, to the complexity issue. You essentially go to the DFT domain, and that results in this case of in the fact that rather than inverting huge matrices, you only invert many matrices of small size. Think of 5 channels and 4,000 coefficients in each channel. So that's a 20,000 by 20,000 matrix. Is not to be inverted, but you rather invert 4,000 matrices of size 5 by 5. And this is essentially what you do in real time then. So if you look at the results, then you feel that you can obtain reasonable convergence, much better, of course, than NLMS. Here is a convergence curve for the system error norms, which tells you how well we identify the real impulse responses. And you get a reasonable convergence with this generalized frequency domain adaptive filtering, which Herbert Buchner and others proposed. And this is here for 2 to 5 channels over time. You see the convergence is pretty slow because this is seconds. What you really hear is actually the echo return loss enhancement, and this is the suppression of the actual echo, which converges much faster to a level of about 20 dB in 2 seconds. Now, it's needless to say that we claim that the reproduction quality with our time-varying all-pass filters is still much better than the others. And we actually verified that by Mushra tests, but I would like to play an example here, and I hope the audio works now. So this is a microphone signal, and it actually is recorded for a distance speech recognition task. Some of you who know German will identify that right away.
Video einschalten bitte. Wie lange dauert dieser
This is
Film?
the microphone signal.
Zeichne diesen Film bitte auf. Was kommt heute Abend im ZDF? Welche Krimis kommen?
That's not you, no? Pardon? No, it's Herbert Buchner.
Video einschalten bitte. Wie lange dauert dieser Film? Zeichne diesen Film bitte auf. Was kommt heute Abend im ZDF? Welche Krimis kommen?
Sorry. Okay, that's basically the effect. I hope you could hear the convergence in the beginning, and you get down to easily 30 dB of echo suppression, echo cancellation. There is no post filter involved. For those of you who advocate post filtering, you can do better even, but in this application, it's still good. Pardon? There's no suppressor. It's just the filter. It's just the 5-channel filter. So you could even do better, of course, but you would not hear that in this application. Okay. Sorry? Mushra. This is simply a perceptual test with where you take, in this case, about a dozen people to listen, and you have hidden anchors where so you have ideal reference signals, and then you all rank relative to that. Okay, there is a real-time implementation running on a PC, and this is actually quite old already. So it was about 5 years ago when we implemented that first on a PC. So nowadays PCs are much faster. But still at that time already we could realize 20,000 coefficients. So what we're doing right now is a little more challenging. It is going from 5 channel to more, and in this case you see a loudspeaker array of 48 channels for wave field synthesis. And Herbert Buchner actually published a generic concept for wave domain adaptive filtering in 2004, which essentially transforms the problem into another domain, namely the wave domain. The idea is here that you do not identify the individual channels from each loudspeaker to each microphone, but you decompose the wave field, which is generated by the wave field synthesis, into the harmonics, in this case cylindrical harmonics of the space, so it's essentially it's Bessel functions in the end. And this transform comes first, and then you go to the DFT domain. And basically what you do is, if in a setup with 48 loudspeakers and 48 microphones, rather than identifying 48 squared adaptive filters for identifying all the elements in this acoustic matrix, then you only need to identify K, in this case 48 acoustic passes according to the wave field decomposition in terms of the cylindrical harmonics. So essentially you bring down the computational complexity from K squared to K, actually a little more than K, but that actually works quite well. We had papers in the early stage on simulated data, but we are now about to implement this in real-time hardware as well. So nevertheless, this is an ideal environment in the sense that the geometry of the loudspeaker array is quite simple and nice to handle, because then the cylindrical harmonics tell you how to do this and how to implement this transform. But the real challenge is to go to, say, listening spaces like your living room at home, where you don't want to have a cylindrical array or a circular array. You want to build the loudspeakers into the walls, and then you need other transforms, and that makes it really hard. So that's still unsolved, but that's something to look forward to. Then the second topic, and I hope I don't run out of time, is the second topic is on beamforming that we use for signal extraction and interference suppression. And I have to say we are not explicitly looking for speech recognition application here, but we did use it for speech recognition as well. Basically, if you look at it, it's simply a signal separation task. So you have this box here, and you would like to separate those signals. And that means you can use 3 domains, either time, frequency, or space. Of course, space requires more than one sensor here. If the origin of the signal is known, and that may be either in time, frequency, or space, then the separability is only determined by the aperture width, basically time, frequency resolution, or spatial resolution. That's what determines how well you can separate the signals. And if the origin of the signal is unknown in these 3 domains, then you can talk about blind signal separation. So, reducing this to the spatial dimension, you have the supervised beamforming for the case that the spatial origin is known, and you have for the case that the spatial origin is unknown, the blind beamforming or blind source separation. And actually, both terms have been used, but blind source separation sounds more fancy. And then most people forget that it's essentially blind beamforming. Let me start with supervised beamforming briefly, and what we see here is just an example for a signal-independent filter and some beamformer, which in the conventional way, which should just be understood as an example what you want to achieve. It looks at 0 degrees, so that's the steering angle, and it's 8 microphones, and actually this can be implemented directly on the microphone array as you have seen it on the laptop. The spacing is 4 centimeters, and what we used here was a Plaindorf-Chebyshev design above a certain frequency, which is about 1200 hertz here. And then from then on you have a nearly constant beam width main lobe. But at low frequencies, you see the spatial resolution deteriorates drastically. Please note this is sensitivity, this frequency, this is space and or angular range, and you see the low selectivity with the low frequencies. In the conventional case, the way to overcome this is often seen as a different way of beamforming, but essentially it's not a different way, it's just providing different filters to the individual microphone channels. And then you talk about superdirective beamforming. It's still signal independent. It's still signal independent filters. And for the same geometry, you see on this heat plot that you can get a much better resolution at low frequencies while still preserving the constant beam width around 0 degree here. This example actually is due to a frequency invariant beamformer proposed by Para. And the problem here is actually that in the low frequency region, you get very sensitive to incoherent noise and calibration errors of your microphones. And actually, that's not on the slides here, but we recently developed a method which incorporates basically constraints on the sensitivity here directly into the beamformer design, so that for a given sensitivity, you can in one shot design the beamformer perfectly. The third kind of beamforming I would like to put forward here is actually a robust version of the generalized side lobe canceller, which we used for speech recognition as well. And actually it was not mentioned on your slide, so it would be nice to compare the recognition results with yours. But as John already mentioned, basically what you do here, and you may remember this block diagram, is a constrained beamforming with a minimum squared error criterion. So it's a second order statistics based criterion in its original version, but you can easily use other optimization criteria with the problem of estimating the higher order statistics. The basic idea is here you minimize the output with the constraint that the desired source should not be distorted. And for that, and the clever idea of the generalized side lobe canceller is actually that the two problems are decomposed. So you have the constraint realized up here, and you have an unconstrained adaptation down here. So that makes it really efficient. But what's important in the acoustic domain is that you adapt the blocking matrix as well to get good quality. The blocking matrix, namely, has to provide an output signal which is a good estimate of the noise. And if this desired source moves here, then it's important that this blocking matrix does not allow any leakage of the desired signal, because this would, the interference canceller which is placed here, would then cancel out the desired signal from here as well. This is actually quite a problem which you need to avoid. So this is why I write here the adaptive blocking matrix is actually quite important. And in order to make this converging quite rapidly, even under double talk situations, so where both interferer and desired source are active, it's advisable to use an adaptation in the DFT domain again. And I will play you an audio example for this here. So first you hear a single microphone with two sources. One is the interferer, and it's at an SIR of 3 dB here. And it's actually the...
Harry looked up at the staff table. There seemed to be rather more empty seats there than usual. Hagrid, of course, was still finding his way across the lake with the first years. Harry...
So let's listen to the output of the fixed beamformer, and please note that the low frequencies usually cannot be suppressed well, because this here is the fixed beamformer, like you've seen it a couple of slides ago. This one, up, this one, right? And it does not suppress low frequency content well. Up. Okay.
Harry looked up at the staff table. There seemed to be rather more empty seats there than usual. Hagrid, of course, was still finding his way across the lake with the first years.
And now finally the output, including the effect of the interference canceller. which should reduce the low frequency interfering noise, interfering speech as well.
Harry looked up at the staff table. There seemed to be rather more empty seats there than usual. Hagrid, of course, was still fighting his way across the lake with the first years.
Okay, and if you measure this, you have an SIR gain of about 17 dB here. But as you could see already, there is still a challenge here, especially if you go to highly reverberant environments. So, as John pointed out already, this way of this version of beamforming does not cope completely successfully with reverberation if it does not have enough degrees of freedom by way of many microphones. So let me move over to the blind part of of this talk, and I will focus only on the Trinicon concept, which has been developed in my group. And first of all, I'd like to look at source separation, and then briefly at de-reverberation, but also at localization, and especially localization of multiple sources and even in multiple dimensions. And we'll see in a minute what this means. So first of all, the blind source separation scenario is given here. So you see multiple sources, multiple microphones. We assume that the number of sources and the number of microphones is equal. And we are looking for a demixing matrix here. GZX, that's actually the same building block that we had in the previous, but now it's meant for demixing. And what you essentially want is you want to extract the desired sources here. So if you ideally achieve that, that would mean you had to invert this acoustic mixing matrix, and then you would get simply a delayed version of the original signal. This is not what blind source separation does, actually. Blind source separation does not blind deconvolution. Rather, it only tries to minimize the mutual information between the output in the best case. So the strongest criterion that you can fulfill for blind source separation is that the minimum mutual information between the outputs is minimized. Trinicon provides a framework which essentially describes this criterion, the minimum mutual information criterion, and it is especially designed for non-whiteness, non-stationarity, and non-Gaussianity of the source signals. And if you look at the cost function for BSS here, it's actually Trinicon is more generic and can be used for other purposes like localization and de-reverberation as well. But if you look at the cost function for BSS, you try to minimize the mutual information between these outputs by looking at multivariate densities of each of these outputs. So here, for example, you have the log of estimated d-dimensional densities for each output. So just imagine you take d variables here and you look at the multivariate density of these d output samples of one channel. Then you multiply all of these d multivariate outputs. So that means the independence of the individual outputs. And you contrast this to the joint density over all the output values over all the channels. This is basically the idea. So, of course, if you write this down as a cost function, you don't have an algorithm yet how to achieve the best filter coefficients. But this is basically the underlying idea for BSS. And there is some averaging here, which allows you to cope with non-stationarity. And also here you have a recursive averaging. So, yeah? Yeah?
It seems like this would be, you made the assumption that you only have two sources, but it seems that that approach would be super sensitive to noise. If you had a little bit of background noise of both, it would mess this up.
I did not mention that estimating these probability densities is, of course, very difficult in general. We all know the higher the order of the moment you estimate, the more sensitive it's to noise. And of course, if you just think of estimating kurtosis, it's a fourth order moment, but the fourth order moment already has a variance of the estimate to the 8th power, right? So you're exploding in sensitivity, right? You can use parametric models, of course, but this is still the generic idea. So whatever you can put into that as models, that will help, and we will come to this. But this basically is the starting point, and everything is basically derived from that by specialization. And the first and simple case that you would look at is second-order statistics, which essentially means you assume Gaussian densities. Also, you may know that these are not representing speech signals well, but nevertheless, it's a way to start. And then you know, for example, that these high-dimensional densities can be captured and entirely described by correlation matrices, and that helps again. So then you, if the source model is just a multivariate Gaussian, then you have simply the correlation matrix to consider, and that also actually leads to a relatively simple adaptation algorithm. The natural gradient, for example, can be computed from the cost function then. So if you reduce the cost function to second-order statistics, you can compute the natural gradient, and you have a relatively simple update rule. And if you look at this here, it actually means you have to invert a matrix very similar to RLS, to recursive least squares. To illustrate what we do here is, you see these correlation matrices for the two-channel case. Actually, whatever we said above holds for the p-channel case, but this is for the two-channel case. So if you don't do anything and you just look at the observed mixtures at the microphones, you would see correlation matrices like this for each channel, and you would see cross-correlation matrices like these off-diagonal matrices. And these are, of course, of the dimension that you foresee for your demixing filters. So if you foresee demixing filters of length 1000, then you still have 2000 by 2000 matrices here. And what this algorithm would try to achieve is to remove the cross-correlation between the channels, which actually means to nullify the off-diagonal matrices. If you want to de-reverberate the signals a little, then you would remove also the outer correlation part of these correlation matrices here, assuming that the inner correlation is due to the speech model and the outer part is due to the impulse response of the filter. And this is what we call partial deconvolution, multi-channel blind partial deconvolution here. And if you completely want to whiten your output signals, then you would perform a complete deconvolution. That's here, a multi-channel blind deconvolution. Then this matrix would be diagonal again. There is a real-time implementation actually since 2004, and we continuously worked on improving it. It's for p equals 2 channels on a PC, and Robert Eichner, I saw him a while ago. He's gone in the meantime. But he's the one who supervised the master's thesis student who implemented that in real time. And there is still a lot to be done, and it's no secret anymore that we work on that for hearing aids, where there are heavy constraints. But even without the heavy constraints of this application, the reverberation is still a problem, and especially the case where you have more sources than sensors. If you think of a cocktail party effect, where you actually have only 2 hearing aids in 2 ears, which may be linked binaurally, but you still are not able to deal with 10 sources. So there's still a lot to be done, but there is some progress underway, and we will publish very soon on that.
Out of curiosity, have you ever tried to have you ever tried to derive the gradients that you would have if you had not a Gaussian circular process, but a circular process?
Yeah. Yeah. You will see this in Herbert Buchner's PhD thesis.
Oh.
Yeah. Yeah. Finally, I hope. Okay. Okay. Anyway, I would like to give you an impression of what we can achieve for the 3-channel case, actually. So, as I said, Trinicon is a relatively generic scheme, and whatever is, and this is actually only one branch, which already makes the assumption that we can describe all this sources by SIRPs, which is exactly what you mentioned by the Meyer-G function. So this is a way of creating multivariate densities based on single-variate densities and extending that relatively simply. And then you have the one branch for the multivariate Gaussians, and you have another branch where you have univariate PDFs. And this is basically branches where you see all the or the most of the common BSS techniques aligned. So this is actually a more generic scheme which has these as special cases. And Robert Eichner actually developed a relatively efficient version for multivariate Gaussians, which I want to play here. You will see the sensor signals, or listen, hear the sensor signals first.
Daddy, listen to what I can do already.
Girl who was loved
1
by
times 1
everyone who
equals
saw
1.
her.
2 times 2 equals 4.
Grandmother.
3 times 3
One
equals
day,
9.
the grandmother
4 times
gave the
4
child a
equals
little
16.
hooded cape.
5 times 5 equals 25.
And because the
6
little girl
times
looked
6
so...
Okay. And if you listen to the output of the BSS scheme.
Okay, finished. Just read it through if it sounds all right. In conclusion, for the interest of all concerned, I must point out that for ecological reasons alone, we gladly grant your request. However, you should prove that you are in a position to keep your word. All in all, your ideas sound very convincing. Okay.
I guess you could hear the initial convergence phase a bit. Let me play the other one.
Daddy, listen to what I can do already. 1 times 1 equals 1. 2 times 2 equals 4. 3 times 3 equals 9. 4 times 4 equals 16. 5 times 5 equals 25. 6 times 6 equals...
Okay. For the sake of time, I don't play the female, but anyway, what you get if you measure the performance, it's about 19 dB in separation gain. And one of the important features here is, which I'd like to emphasize, you basically have no distortion of the desired source. So you can, there is a slight coloration, but there is no distortion like you have it usually in noise suppression techniques and spectral subtraction. Okay, so let me move over to de-reverberation. And de-reverberation is here considered or depicted as a single channel problem. We actually look at it in the multi-channel problem, in the multi-channel setting. But the main idea is here really that you consider this speech signal as being a correlated signal where the first part of the correlation is due to the vocal tract and the rest is due to the room characteristics, which means you would like to preserve these diagonals in the cross-correlation matrix, and you would like to get rid of the outer diagonals. That's a relatively simple idea, but it's relatively hard to put this into an efficient adaptive algorithm. So because it asks for another constraint in the adaptation. Nevertheless, you can do this, and please note, as in the blind source separation context, we use filters of length 1000 at a sampling rate of 16 kilohertz. Here we have again two channels. And the nice thing about this scheme is that it of course does separation and de-reverberation at the same time. And actually the separation is even improved relative to the mere BSS algorithm. And the de-reverberation is also clearly stronger than with, for example, a delay in some beamformer. But of course, if you only have 2 mics, the delay in some beamformer will not give you much. I'm not sure whether you can hear the effect in this room, because the original signal is not too reverberant either, but let's try.
We will achieve a more vivid sense of what it is by realizing what it is not. It's not easy to create illuminating examples. The side ones are ½ inch narrower. We will achieve a more vivid sense of what it is by realizing what it is not. It's not easy to create illuminating examples. The side ones are ½ inch narrower. We will achieve a more...
Okay. So basically this is how far you get without any extra measures, without any subtraction and post-filtering or equalization of the spectrum. This is really what comes out of the Trinicon algorithm. And of course, if you feel that there's any coloration, you can still equalize that. Let me look at localization briefly. And I see I'm almost running out of time, but we're getting close. Okay. We can use this blind scheme for localization of multiple sources as well. And the idea is essentially, again, relatively simple, because if you consider this source here and the effort that is done by the demixing matrix in BSS, it means that if you want to separate these two sources from each other and you want to get S1 here, you need to identify filters here in these two passes, which essentially are equal to these two channels. So this acoustic channel should be modeled by this one, and this one should be modeled by this filter. So if you look then at these filters and look at the main peaks, you will find the direct acoustic path. And the peaks of the acoustic path tell you the relative delay between the two signals, and that is an indication of the direction of arrival, and then you can basically find the source location. That is simple as long as you have only two sources, and it can actually be seen as a generalization of the adaptive eigenvalue decomposition algorithm that Benesti published in 1999. If you have more than two sources, then you can compute something like directivity patterns at the output of these of the BSS scheme. And these zeros that you will find, they point to the suppressed sources. And so you only average over several directivity patterns and you get a pattern of all the suppressed sources, and the suppressed sources will tell you the locations. So that's basically a DOA estimator. And that works in the overdetermined case as well. So that's the case when you have more sources than you have microphones. You can also generalize this to multiple dimensions, because if usually localization is only seen in a plane as a problem. But of course, sometimes you want to be three-dimensional, and then you simply combine several BSS units, maybe one in the vertical plane and one in the horizontal plane. And the nice thing about BSS is that at these outputs, you have the original signals, the separated sources. So it's relatively easy to correlate these outputs and, for example, resolve all kinds of ambiguities which you would get if you have a set of angles for your desired sources in one plane and another set of angles in the vertical plane. You would not know how to align those. But with the signals to correlate here, if you take these signals and correlate them in the two planes, then you find the proper pairs of angles. Nevertheless, there is still a lot to be done, because we are also interested in making this scheme reacting very fast to short acoustic events. That means, for example, to shots or to glasses falling down. And then you usually don't have enough time to converge to reliable solutions.
So is there some kind of trade-off you can make? Because
Sorry?
I'm wondering kind of trade-off, because I mean, if you're doing Trinicon for localization rather than for separation, I imagine you can use much shorter filters.
Right.
But then your separation isn't as good to do.
Right. And then that's basically what we do anyway. So we have, I don't talk about implementation for certain applications, but you would have, at least for localization, as you say, shorter filters. And then you're, of course, converging faster, but the result is not as reliable as you like to have it. So, of course, that's the way to go, but it's still not solving the problem completely, because the reliability suffers. Okay? So let me finally go to localization of multiple sources in another domain, namely in the wave domain, and that brings me to the nice little array that Heinz Teutsch built a while ago, where we combine basically our idea of wave field analysis, that means describing the acoustic wave field in terms of cylindrical harmonics, with the techniques that are known from array processing, namely the subspace methods. Usually these subspace methods are meant and most effective for narrowband signals. But of course we deal with wideband signals, and fortunately the wave field decomposition gives us a description of the wave field which can be handled as if it were narrowband. So we can apply these methods here. And we use, again, cylindrical harmonics, and this is very close to what Gary Elko proposes as eigenbeams when he uses beamforming, when he uses these arrays for beamforming, but we use it for source localization. And actually, then we use the typical algorithms for subspace localization, that is music or Esprit. Actually, Esprit turned out to be much better for our case. And that allows us essentially to localize m-1 sources if we m-1 sources simultaneously, and m defines the number of cylindrical harmonics that we consider, and actually we could localize up to 5 sources here with this arrangement. And this is a very small device, as I said, about 10 centimeters in diameter. Again, this is not complete because these subspace methods are also assuming stationary sources, and you have to be quite reliable in estimating your covariance matrices. But if you can't do that, then you have to find some improvement on the algorithms to deal with non-stationarity. We are on this road, but we are not yet at the goal. And it's not yet solved completely. And finally, again, reverberant environments are another problem, which is not completely solved here. It works in mildly reverberant rooms, but not in strongly reverberant rooms. If you put it in here, it would probably work. This is not a bad environment for that purpose, especially if you put the microphone array onto the ceiling here, that would work. But if you go to nastier environments like train stations or large halls, then this doesn't work that well so far. So let me conclude. What I wanted to show here is the plain acoustic human-machine interface still offers a number of major challenges, which can both seen as signal separation and system identification tasks. And the reason why this is still a problem is the acoustic environment which we deal with is highly complex in terms of number of degrees of freedom and its time variance. And also in the natural environment, for these natural interfaces, we usually miss the reference signal. So we have many blind problems. And this is one of the main things. And here is the list of what we've been looking at so far: multi-channel acoustic echo cancellation, beamforming, source separation, de-reverberation, and localization. This basically concludes my talk, but I would like to add to John's statement. Reverberant environments are really still one of the many challenges which we have, and that's the ones that we want to solve in the future, that we see as the next major task. And we have been working for that on that for a while now, but we are still pretty far away from perfect solutions. That concludes my talk. Thank you very much for your attention.
Thank you, Professor Kellerman. We have time for a couple of questions.
So BS's type of signal processing obviously is going to go to cell phone, right? Because Qualcomm recently bought this company doing BS. I just wonder whether this kind of signal processing technique, are they going to go to digital hearing aid in the mainstream, or is there something going on already?
Maybe I didn't get your question.
Digital hearing aid.
You mean which kind of processing is going into hearing aids?
Yeah, in terms of their visibility.
I don't. I cannot talk too much about that. Okay. But certainly, hearing aids are a very interesting area, and it's highly constrained, and it does not allow for any imperfections in speech quality. So hearing aid manufacturers will not allow, say, strong noise suppression with artifacts. That you will not get.
So the design is very different from the cell phone.
The cell phone allows much more, say, artifacts, and whatever is cheap will be bought, right? So it's a bit different, but nevertheless, we're not only focusing on hearing aids because all the wavefield synthesis stuff, of course, is obviously not suited for for hearing aids. So, but blind source suppression is obviously something which is very well apted to hearing aids, because the blindness does not only mean you're blind for the source positions, you're also blind for the sensor positions. And this is actually a feature that is important for hearing aids, because hearing aid wearers will not type in the distance between the microphones first, or the say the look direction of the small arrays they have behind each ear, right? So that's for these algorithms, for binaural algorithms, you're actually blind with respect to the sensor positions as well.
So in that case, I mean, whether the distance within
but
one single ear with different microphones, is it going to be too small?
It's very small. There are a couple of issues. I referred only to 2 microphones in the blind source separation problem. But of course, nowadays hearing aids have up to 3 mics at each ear, right? And they are very closely spaced. They are highly superdirective beamformer, right? And so there are a couple of issues in the interaction of those with with blind source separation, for example. But this is, I would say, that's a very specific area.
More questions, John?
Okay, one comment and one question. So we tried out the Hoshiyama beamformer as well as the beamformer developed by your student Wolfgang Horvath.
Yeah, if it were the same, we wouldn't have published it, right?
No, I didn't say it was the same, but we tried it out and we were sort of embarrassed because we couldn't publish the results because they weren't better than the MMSE beamformer.
That depends on how you implement this, and MMSE is a flexible criterion. If you put the constraint into it, then it's different.
Too, but anyway.
No, MMSE is a different criterion. So if you take a plain MMSE beamformer, you don't have the constraint in it, right?
Okay. The question was, okay, you made the comment that de-reverberation is different from speech separation,
right,
or source separation. But there's this result from the ICA world, and they show that essentially neg entropy is related to mutual information.
Yeah, that's no doubt about that.
If you minimize the mutual information, you're essentially maximizing the neg entropy.
Right.
But you saw from my results that reverberation increases neg entropy. Or sorry, decreases neg entropy.
Yeah, that's. But this is a byproduct, I would say. It actually. Oops. Let's see.
So my question is, doesn't the distinction go away between reverberation, de-reverberation, and source separation? Doesn't that go away if you consider non-Gaussian statistics?
No. If you look at this here, so this is the BSS cost function, right? So that's this. That describes mutual independence between the outputs, right? Now, if you want to de-reverberate, right, then you have to put into these estimated densities a source model for your signal and a model for your reverberation in each channel, right? Then you can describe this as a, say, a multivariate density with a separate term for the source model and a separate term for the impulse response, right?
So maybe we should talk about this later on, but there's a result from the ICA world that shows that if you enforce the constraint that the final sources, the sources that you separate, must be decorrelated, then maximizing neg entropy is equivalent to minimizing mutual information.
That holds for scalar mixings. We are not talking about scalar mixings here.
Yeah, but results that I showed demonstrated that when you reverberate a signal, it becomes more Gaussian.
But this is on this the case if I reduced my dimension d here to 1, right? So that's a special case. If you go here to 1, then you're fine. But this is explicitly not done here because we know that our outputs are correlated signals, and we treat them in the time domain. Right? The cost function is derived in the time domain. The implementation is done in the frequency domain. We don't care. Right? We can do anything in the DFT domain as long as we are careful. Right? But you have to be careful, of course. But nevertheless, the cost function is on the time domain samples. And then you go to the frequency domain for implementation purposes. And this is a very, very fundamental part of this concept. Unlike all these, I'm getting nasty now, sorry. See, here is the unconstrained DFT domain BSS world. And here is a block which I see as a dark hole, where you do all kinds of repair mechanisms to, for example, resolve the ambiguity problem. And this is you.
Okay, so Walter, we can be nasty at lunchtime.
Unfortunately, Professor Kellerman is already
I don't want to discard these algorithms in principle, but they are all they all set d equal to 1, and then they need something to realign the frequency bins, right? And that basically can sometimes bring you back, as in the para domain, to a model which is essentially in line with starting with univariate PDFs and so on. So you can go back a little bit, but many of the algorithms are really using repair mechanisms, correlation between frequency bins, and so on, right?
I'm sorry, we have no time for more questions. The next talk is about to start. Professor Kellerman is late already from the airport. Yeah. Let's thank him for the good.